and welcome back. Today we are going to learn a relatively easy topic in chemistry, that is electron, energy level and atomic orbitals. Previously we have discussed the particles in an atom and atomic radii. You can watch this in the previous videos. Isotopes and how to calculate the relative atomic mass of isotopes. And now we are going to learn the electrons, energy levels and atomic orbitals. Let's start with this one. So, what is an electronic structure, or what is an electronic configuration? So, when we talk about the electronic structure, the electrons are arranged in different shells. Keep in mind that the first shell is quite smaller in size, so it would have smaller number of electrons or less electrons, while the outermost, or you can say the fourth, fifth, sixth, as the number increases, the size increases, so the shell becomes bigger. It can accommodate more number of electrons. So this is known as electronic configuration. So how do we define it? Basically, electronic configuration is the arrangement of electrons in an atom. So there are four quantum numbers which describe the position of electron. So our main concern are with three. So very first one is the principal quantum number. This is actually the shell number in other form. So whether it's the first shell, second shell, third shell, whatever the shell is or whatever the orbit is, that is your principal quantum number. Next is the azimuthal quantum number, which tells you about the subshells. Like for example, you can take this as an example. You have a house that is a shell. Now, in a house, we have different rooms. Those rooms are subshells, and those in those rooms, different people are living. So those are electrons. So it would be easier to understand that it's a bigger one, and then we have rooms, and then we have individuals who are living in those rooms. So third one is magnetic. We are not going to discuss this in this video, but we are going to discuss the spin quantum number, that how electrons are arranged according to the spin. So electrons are arranged around the nucleus in the principal energy levels, or the principal quantum number. That is the shell. That is the main, like house is a house number one, house number two, whatever. Let's move to the principal quantum number. Schrödinger was the first one who explained this, who actually gave the concept that the main energy levels of electrons, and he named them as a principal quantum number. The principal quantum number starts with 1, 2, 3, 4, whatever the number of shell is. So when we talk about the first shell, it's a small house. It has lesser number of subshells. The second shell would be a bigger house, so it would have more number of rooms. Third would be more bigger. It would have more extra, more rooms. As the size increases, the room number increases. So, so the individuals. So the principal quantum number also describes the distance and the amount of energy of electrons in an atom. So we say that this is the first level. The electrons are at low energy level. So this is our second energy level or third energy level. So the energy increases basically. The lower the principal quantum number, the closest the shell is to the nucleus. Let's look at this diagram. When we talk about this, look over here. This is the first shell. This is the quantum number, principal quantum number 1. So this is our first shell. So it's closer to nucleus. And if we talk about the higher value, it means it's far away, and definitely is far away, the energy level is high. Take this as an example. For example, you are in a classroom. If you are sitting close to the teacher, take this an example, the nucleus is the teacher or the teacher is the nucleus. If a student is sitting close to teacher, that teacher would have more control on the first row of students, and the energy level is quite low. They will follow whatever the teacher says. While if you talk about the back benchers who are sitting at the back, they're not going to listen. Their energy levels are very high. They are least bothered. So when this number of shell increases, the electrons are far away from the nucleus. There is less hold, so the energy level is very high. Now, how many electrons can we accommodate in these shells? So we have a formula like 2n square. So when we talk about the first shell where the value is 1, it would be 2 into 1 is 2. So maximum 2 electrons can be accommodated. If it's 2, then 2 square is 4. 4 into 2 is 8. So maximum of 8 electrons can accommodate in the second shell. If we take here as 3, 3 square is 9 and into 2 is 18. So maximum 18 electrons can be here. If n's value is 4, it would be 16. 16 into 2 is 32. A maximum of 32 electrons can be accommodated in the fourth shell. But keep in mind, the sequence can be different because we have different rooms. Maybe the rooms in the third shell won't be that much comfortable. The electrons might want to move in the fourth shell before completing the third shell, and we are going to learn this further. So what are the subshells? Now, how to fill the rooms? The azimuthal quantum number actually tells you the subshells, how many subshells are there in the first shell. So there are total 4 subshells. We name them as S, P, D, and F. These are the different shapes because they lie in different dimensions, they have different axes. So these are the shapes of the subshells. So when we talk about the energy levels, now how they are going to accommodate. So take this as the first floor. This is the first floor, this one. So this is house number 1 and this is the first floor. The electron is going to accommodate over here. Now this is house number 2. It's first floor and second floor. House number 3, first floor, second floor. Now the third floor, now this house is not having any elevator. They need to climb up the stairs. So the energy level should be very high. So this has more energy as compared to the first floor of house number 4. That's why I've told you in the previous slide that before filling the third shell, the electrons might move to the fourth one. So there is a very easy way to learn the order. It's like school, public school, or public school, or divisional or district public school, or district public school. You just name them, or the FDPS. So how do we name this? This is like 1. Let's number them. 2, 3, 4, and 5. Now the next one. P starts with the 2, not with 1. So second house would have a second floor. So 2, this is 3, and this is 4. D would start with third house. So 3. Now look at the energy levels. It's 1s, then 2s, then 2p, then 3s, 3p, 4s, 3d, 4p, 5s. So this is the easiest way to learn the electronic configuration or to accommodate the electrons. School, public school, public school. Repeat everything. You need to say twice, like school, school, public school, public school. DPS, DPS, FDPS, FDPS. This is the easiest way to learn how the electrons are accommodated in the different subshells. Now, if we take a look on this, this is the first shell, this is the second shell, this is the third one, this one is the third one. So when you count the number of electrons, you need to count the electrons of all the orbitals. Keep this thing in mind. Clear? Let's move to the next one, like how the shapes are different or how the electrons are arranged. But before that, let's take a small break and discuss this in detail in the next video. Welcome back. As we have discussed in the previous video that what are shells and how electrons are arranged. So we have different houses, house number 1, house number 2, 3 and 4, and they have different the stories, the first floor, the second floor, third floor. So they would have different number of floors. So the number of electrons or the number of individuals that are living in these houses also differ. So let's move to the shape of this one. The first one is the sub level one. It has a very well defined shape, or a clear shape, or a sharp shape, and that is mostly spherical. That is round. Not a circle, but around. It's a spherical, just like a ball. Not a 2D shape, it's a 3D shape. Then second one is the P1, which is the principal one, and it has a dumbbell shape, the one with which you lift the weight. Number three, the diffused one, because it has so many dimensions, so it's just like a clover leaf. We will discuss these shapes later. And then F is the fundamental one. It would be in so many axes that it is difficult to explain. Let's move to the spin quantum number. Now, what is spin quantum number? So, how the electrons are arranged. Keep in mind, when we fill in the shell or fill in the subshells, we place them separately first. For example, you are living in a hostel, or like, and you have three rooms. So when one person enter, that is going to fill the first room. When second person enter, it is going to fill the second room. When the third person enter, that would definitely prefer a separate room than to live with the first one. So the number of individual, first of all, one electron would be assigned to each of the orbital. Then if now the fourth person comes, that has to share the room. So that's why they are paired. This is actually the spin quantum number. Like the two electrons would be in the same orbitals, and now they are not going to be in the same spin. They are in different spins. If one is clockwise, other would be anti-clockwise. This is the spin quantum number. So in one orbital, the electrons could not have the same spin. They cannot be like, both cannot be clockwise or the anti-clockwise. One needs to be clockwise and others need to be anti-clockwise. So this is how we define them. The anti-clockwise clockwise spin is positive, while the clockwise spin is negative, and we name them as half. Clear? Let's move to the arrangement of orbitals. So what is orbital? It is basically the space, or the volume of a space in which there is 95% chances of finding an electron. And we have discussed in the previous video as well, who actually gave the concept Schrodinger. So electrons can be found above or below the orbital. It's possibility that they can be here, they can be here, here, or here, so, or here below the orbital. But probability is very low, because they follow the path, a certain path, because they need to be connected with the nucleus. So the nucleus have a control on those electrons and keep them in a certain, like, a certain pathway. Next one is the shapes of orbitals. As we discussed earlier, s orbital is quite spherical, and when the probability of finding electron in between two orbitals is zero, because they have to be like perfect in shape. They can be present here, 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 but they cannot be present here. They cannot be present here. So it's very sharp shape, as we have discussed earlier. So the probability of finding electron is quite easy. Now the p orbital, that has three axes, x, y, and z. So what is x, y, and z? The px one, this one on x-axis, y1 on like this axis, the vertical one, while the z1 is on the like this axis. Like, if you look at the corner of the room, you can easily find the three axes, the first one, second one, and three one. So these are the different axes, and they are like dumbbell. While if we talk about the d orbital, now look over here, the axes are quite difficult to understand. So first one is, let's say, xy. One is in the x, other one is in the y. This is the shape, xy. Then yz, this is y and this is z, and they're present in these planes. Then xz, then dx square minus y square. This is a plane, and and there is a huge calculation behind this one. And this is d square. This is the shape, and this is quite difficult to draw these shapes on a paper, definitely, but you can easily draw dx, dy, and dxyz. So these have five orientations and they are like double dumbbell. Now the F1 is very difficult to draw because it has multiple planes. Now the arrangement of electrons we have discussed. It's school, public school, DPS, FDPS. Okay. Now let's write an example. For example, we have oxygen. Let's say oxygen. Oxygen is 8. So let's just name the orbitals first. School, school, public school, public school, and then GPS. But I don't think so. It's going to, like, we are going to use this one. Now let's just name them 1s, 2s, 3s, 4s. Now 2p, 3p, 3d, and 4p. So first of all, we have to name the orbitals. Then what we have to do, we are now going to adjust the electrons. Okay ji, first house, electron number 1. Now no other option. If the other participant is adding in, it has to adjust with one with opposite spin. Now 2s, first of all, electron are going to enter this one. It would be like this. Now if we talk about this P1, this P is going to be separated in three different axes: Px, Py, and Pz. Clear? Now let's arrange the electrons in this one. Now how many electrons are left? We are left with 4 electrons because 4 are accommodated, 2 here and 2 here. Let's arrange the 4 one. First of all, the electrons are going to arrange separately. They are going to be accommodated in the separate rooms. Now what happens with the fourth one? The fourth one may have an opposite spin and may accommodate in px, like 2px. So it would have 4 electrons with 3 different rooms, one with 2 electrons and the other 2 with one electron. This is how the electrons are arranged in oxygen. Now let's discuss the titanium one. Let's go to the titanium one, and now you are going to find its electron number, or you can say the proton number. Just find the proton number and tell me in the comments what electronic configuration have you figured it out. Just do this first thing. Just name the shells like SS, PS, DPS, FDPS, whatever. Now name them. Okay, this is, for example, we say 1s, 2s. Now these will be assigned to 2p, 2px, 2py, and 2pz. Then 3s, then 3px and 3py, 3px, 3py, and 3pz. Now next one is the 4s, then 3d. These 5 belongs to 3d. Let's say 3d xy, 3d yz, 3d xe, 3d x square minus y square, and 3d z square. Clear? This is how you arrange the orbitals. Now fit in the electrons based on the electron number and tell me in the comments, and I'll be sharing the result shortly. Let's arrange the electrons. I hope you have found the proton number. Okay ji, the very first one is the 1s, so there would be 2 electrons. Very simple. 2s, 2 electrons. Now let's fill the p1. 1, 2, 3. We have abundant electrons. Let's pair them up. 1, 2, 3. Now then more electrons are available, so it would move to 3s. First of all, we are going to fill in the first floor. Then we have more number of electrons, so we can place them separately. We're still left with more number of electrons, so we can pair them up. Then the it's difficult to climb up the third floor, so let's fill in the fourth house. The person move to the next house. So 2. Now how many electrons are left? So we are left with only 2 electrons. Now we have to fill in the d subshell, but those would be in two different subshells, not in the same subshell. I hope you have you got it right, and you have, if you made any mistake, you have made the correction. This is all about the electronic configuration and how we arrange the electrons. So next one is the free radical. How do we explain the free radical? Now, if we talk about the free radical is always the unpaired electron. For example, if we talk about the chlorine, you might have heard ozone depletion is because of the chlorine radical, because we have so many chlorofluorocarbons and it causes a great damage to our ozone. So the free radical, it's very reactive because it has unpaired electron. It has a lot of tendency of the reaction. So that is the, we show it with dot. For example, the chlorine one, chlorine dot. That is, if we talk about the shells, it would be 2, 8, and 7. It would be 1s2. This would be 2s2, 2p6, sorry, 2p5. When you talk about 5, 2p6, sorry, then this one is 3s2 and 3p5. Let's make an arrangement in this one. px would have 2, pz would have 2, but pz is going to have 1. Now this unpaired electron makes us a free radical. Now let's move to the periodic tables, how they are arranged. The very first two, the first group and the second group, they all have electrons in the s subshell, so they are called s block. From third till eighth, those have electrons in the p orbital, so they are called as p block. The transition elements that are present between 2a and 3a, these are basically starting from 3b here and 2b here. Those are have the electrons in the d block. As we discussed, the titanium would be in the d block, and they have electrons in the d subshell. And they are, why do we call them transition elements? Because they show some type of transitions. The electrons move from one shell to another because they have high energy. And then the f block means their electrons lie in the f block, the valence electron, the outer electrons. Now this is all about the atomic orbitals. See you in the next video.